All right. So today we are going to talk about how to spread the ideas of IAT, especially in the recent concept proposed by Cohen and Tononi relations, but also, even before that, like IIT 3.0. So we are talking about, we have Alex and I have been thinking about collaboration on analyzing the empirical data using ideas of IAT, and then we have encountered a couple of troubles which some other people may be also interested in hearing. So that's the reason why we are doing this. So maybe Alex, do you want to start with your problem statement?
Yes. So what happened, I can probably start what happened to my own experience, which is that as somebody who's collecting a lot of neuroscientific data and is interested in consciousness, I had an aha moment understanding integrated information theory 3, basically the formalism that goes with it and the power that goes with it, based on your paper, the Leung et al. 2021 paper, where you analyzed local field potential data from the fruit fly, anesthetized and awake. And you showed that using the formalism provided by Pyphi toolbox that incorporates the IIT3 mechanisms, that you got very interesting results out of these data. And of course, what percolated was, okay, what are the limits of that? What else can we use it on? And what first caught my eye is that the algorithms themselves, the formalism itself, may be interesting to systems neuroscientists, even more generally, even if they're not interested in consciousness, because it allows for the computation of causal powers quantitatively, given existing data. So it seems to do what a lot of people think is impossible, that you have observations only, and you think you can only find correlation in the data, but using these very clever ideas of introducing cuts in the system and investigating the effects of the cut onto the system itself, you can intervene, you can make interventions, which is necessary to look at causal interactions and derive causal effects and causal powers in your data. And so even more interesting, you don't just have to do it for pairwise interactions, not just for pairwise points in your data, one measurement here, one measurement there, but you can do it for higher order interactions as well. And so one idea may be that in order to get IIT to become more popular is to show people that this formalism, these algorithms, these ideas are highly useful. And even if you're not interested in consciousness, familiarize themselves with these tools, and that would lower the entry barrier for people to understand the theory and understand the power of integrated information theory in explaining consciousness, and therefore hopefully further spread the word that you can study consciousness scientifically and rigorously and mathematically, which is what the word on the street seems to be that you can't. I think you're muted.
Yeah, because I was typing. So I basically share your ideas and also strategy. And what we have been doing is to try to provide some kind of tutorial videos for IIT3, and also Angus's paper, Leung 2021, has some toolbox and also data that comes with it, so other people can replicate that. And I think we just need to move gradually as sort of within our capacity to repeat that. I think the IIT itself has been so far mainly interested by philosophers and also computational scientists or theorists in general, right? Who do not care about the empirical application of this theory. So most of the IAT testing or investigation has been done on the very small, systems, and that's also that makes it difficult to see its relation to, consciousness. And so, that's why we took a step, to apply it to even, it's a fly system. We thought that that would be still meaningful, and that's the reason why we did that. And then I think we need to just accumulate these kind of things gradually. So what we should probably do is to really try to help any people who are interested in using this kind of thing, and then try to apply that as much as possible. So curating our toolbox and also data, and maybe extend the collaboration to those people who are interested in applying this. So that's the one strategy. And exactly the reason why we are having this conversation is exactly that you are interested in applying this, and so we want to help this. So that's that it's kind of frustrating because it takes time, and seeing the impact or feedback is slow, but still we need to do that. That's my kind of attitude.
Yeah, and I think that what you said, the other point may be that if you really think the theory through, you would like to use that formalism and to compute those kind of measures, such as phi max, for an entire, say, human brain or entire system that we know or are highly sure has conscious experience or is conscious. And so it can seem frustrating to use these algorithms on very limited systems where phi isn't very high. And so I think that too, it would be helpful to not be discouraged and to start using it on simple systems, as is done in the papers on integrated information theory, with a few AND gates and OR gates, relatively simple systems that you can think through and understand, but then do the same when it comes to empirical data, and not shy away from, even if you only have a few neurons that you measure, to still apply these kinds of measures and see what we learn. And basically not wait until the point that we can accomplish that we have data for each and every neuron of a human brain. So I think that would be another important step right here. And
yeah, so for that, I start to diverge the view with you, right? So, I understand that you have been kind of criticized by people when show our paper to somebody. Okay, then oh, okay, that's interesting, but it's still fly. So why does it matter for our consciousness? I take that. However, history of the neuroscience is really in fact single neuron study has been a hugely impactful, right, in many ways. But what single neuron study, what it does is really just looking at one neuron's behavior or correlate with a very small proportion of the stimulus that could potentially activate this particular neuron in an extremely artificial way, like train the monkey in the dark and not moving, and then still we could understand something about how the neuron works in the system neuroscience. So some people who are watching this video who have never heard of the systems neuroscience would be very surprised to see that the majority of the system neuroscience, especially in the monkey field, is all about the one neuron of a behaving monkey, right? But the reason why we can kind of understand this single neuron is that the assumption that the single neuron is connected with the rest of the things, and understanding the relation of that single neuron with the rest of the things, potentially through our understanding of the anatomy and also the behavior and how other single neuron study has laid down on the sort of the processing steps through computational modeling and things like that. So, that's why we can start to understand the whole picture, even with the single neuron recording. So I don't think, you need to be discouraged by the kind of the statement that, oh, fly, okay, that's too small. It doesn't matter for consciousness. If you talk to the fly recording person, the underlying mechanism of the anatomical connectivity in a fly brain is no, I wouldn't say it's very similar, but the underlying sort of the architectural principle is definitely some kind of correspondence with the vertebrates, like sensory neuron outside, and then these are processed in the medium and the higher systems, and that higher system tend to have an invariance, and they talk to other systems, and then there is some kind of memory system, and all these are also integrated with a motor system and so on. That basic architecture is common across the any kind of moving and the reproductive biological systems, right? So that's very different, I see, in applying IAT into the simple simulation system versus even flies or C. elegans, because the amount of the possible systems that we can test or think about in the universe is really immense, immense to the sort of the power of the immense, really, right? But a biological system is extreme small subset of that, almost like a point. And within that, if we can find some kind of common principle with that, I wouldn't be worried too much. So that's one answer, right? About single neuron, simple whole system. And then another thing is that the quantum mechanism, whole entire quantum mechanics has been initially built out from just a single atom, right? Or one atom interacting with another one. And but when we try to extend that to the entire universe, so far at least as the physicist said, we can't find any kind of contradiction with that. But nobody has, or nobody can build this entire reality based on the quantum mechanism, because even starting to build some small entity with based on the single neuron, single atom, two atom kind of interaction of the quantum mechanism as Schrödinger's wave equation is impossible. But we can still kind of build out the whole and then still understanding. And the reason probably why we can do that is something that I started to think with the category theory. And so category theory is probably a very nice bridge to think about how we can go from the parts to whole, right? As far as I know, and it seems like this is agreed on, many mathematicians and computer scientists and so on, category theory is the most proper mathematics to study the structure. And interesting thing about category theory is that many of the concepts in the category theory comes with a kind of idea that is almost like an atomic model that looks like this. So for the the model of the carbon atoms, if you remember from the high school chemistry, right? When you another way of thinking about atoms is like this one, right? And when I see, sorry, it's getting long, but when I'm reading some philosophical discourse or explanation of the previous Gestalt psychology and also atomic theory of consciousness or qualia, or structuralist thinking of qualia or consciousness, it seems like what they have been criticizing is that qualia as something like this type of atom, right? Like single thing that is not that exists on its own and that's not get affected by others and so on. And if they really believe that, and then as the Gestalt psychologists criticize, no, conscious experience phenomenology is not a bundle of this type of atoms. No, that's not the case. And the reason is that the fundamental understanding of the atom itself was wrong at that time. Atom is something that is like this way, for the, in the case of C, it has a, way to interact with others, and the specific interaction rule predicts how this, thing, C can become like a graphite or diamond or something like that. Because of this structure can be connected like this way, or just combined differently, right? So what category theory does is that to describe some kind of parts, but how the parts can be connected with the other inclusion. So in the case, for example, just one tiny example of the way category theory define the product, right? When you think about product in this way of idea, what you can think of is something like this, right? A times B. And that's the sort of atomistic kind of thinking of product in my mind. But in the case of the category theory, how they define product is this thing together with a pair of arrows like this way. This is something that I struggled really, very difficult to understand in the beginning, because, when you're introduced about some kind of concept, it's very weird to hear that something is characterized not as it is itself, but its relation to others. But, with what is not specified, right? But this is actually exactly like neuron as well, right? When you are recording a neuron as something like this entity, you never understand the whole system. But if you understand neuron like this way, it is connected with this and then situated here, then you can understand potentially understand the whole. But to do that, we need to understand the mechanism or rule of how it's related to others. And as long as you're kind of humble to understand that, oh yes, what we are looking at is a parts, but how the parts connect to whole is understood in some way, then even looking at the small thing can reveal something about the whole. That's my kind of idea.
Yeah, that's extremely interesting. Yeah, thank you. That was very helpful and very interesting. I mean, so basically, part of that is, I think, what you're getting at, that when we bring it back to integrated information theory, that we treat it as a mechanism, as literally as information being integrated, and that itself is interesting to study. And you can study that on a smaller scale. I mean, that's independent of what you have right here, which is ingenious. I find it very interesting, your point about thinking about the neuron not as a single entity, but as what it means within the system as a whole.
Yeah.
But this idea that we can study mechanisms, and therefore we can start small. I think that is very, very exciting.
Yeah, so if I translate this kind of idea into sort of an IIT like idea, right? Then so when we talk about this two neuron system like A and B, and then that is interacting like this way or that way, for example, or connected in this way with some specific thing. Thinking about this is all right as a starting point, but I would say that the more important thing is to also realize that this is also embedded in other things, right? So two things is something that is only affecting A or only affecting B, and also jointly affecting A and B, right? So without embedding A and B in this context, it's very difficult to understand this. And then you said something about this, intervention, right? Without an intervention, can we actually analyze the cause and so on? So we can't, to be honest, but what we are hoping to do, and also what we plan to do, is to investigate whether under many different kind of situations, if the behavior of this, a part of the system is as predicted, then it corresponds to this, the true sort of the causal mechanism that is embedded in there. But maybe I should actually talk about it later or at other time about that. So anyway, even if you realize that this AB system is embedded in this way, if you just think about the number of the parameters in this system, right? Like there is 1, 2, 3, 4, 5, 6, 7. At least you need 7 parameters to describe this system, and that's a really huge number of parameters for 2 neurons, right? And also, when 2 neurons are embedded in different contexts, that means that this 5, 6, 7 parameter actually changes. Under this fixed background condition and fixed output from others, then the relationship between A and B actually changes, even if there is no plasticity between A and B itself. But I think if we have a huge amount of data available, as it is from Alex and Allen Institute data, or something that you are also collecting, I think it's possible that A and B relations can be classified in some kind of interesting patterns. Like most obvious would be like A and B not really connected at all, right? And then if that's the case, then by default, A is affecting on itself, A, and then A is affected on by A itself, and B is affected by B, and then like this way. And so there's no relations, no integrated mechanism of A, B together, and so on. So it's super simple, 5-0 system. So we need to think about how many of this is the actual proportion in the neural system. Right? Then the second thing would be like probably the most dominant type of the connection is probably the self connection, I think, usually, but also A to B and that kind of unidirectional connection, right? It's probably exists a lot. And then when this happens, A and B physically connects each other, but only one way, then what kind of relations and also mechanism can emerge? Many people kind of misunderstand that feed forward direction of the parts completely predicts that there can't be integrated information, but that's not the case. Under some kind of situation, it can have an integration, and so exactly what is something that we need to understand. And finally, most interesting situation would be like both connection, right? But both connection can have also many different kind of the patterns. Sometimes AB as a joint sort of the mechanism doesn't exist, which is very weird, but it's true. And so we can classify many ways of empirical combination of the neurons and so on. And then we can also step to 3 neuron situation, ABC. And starting from here, I think it's already quite interesting, but like a link to quantum mechanism is quite interesting. I really find these days, because like many things starts to break down or starts to become interesting when you start thinking about 3 things. Like, I've been quite inspired by the Carlo Rovelli's Helgoland. Have you read that? Yeah, so that it's translated in Japanese, and then its title is actually much better. It's Japanese version of the title is that everything is relational. And there he talks about this, a superimposition of the two systems, or two waveforms make only sense when there is another observer or another interacting system. So something, to describe 2 things are interacting, you need a third person or third entity. Something like that happens also, for the neuron system and recording, I think. So that's, it's not really well articulated, but this is something that I've been thinking these days. So the point is that building from small to large with the idea of how this small thing gets connected to the whole is not really, contradictory to the horizon. And also it is a much better extension of the reductionism, right? Not really cutting things, but also being cognizant that, we are cutting, and how the cut affects the whole needs to be, mindfully, investigated.
Again, that was really great, very interesting. Can you, your starting point where you said that A and B up there are embedded in a greater causal network, if you will, that those are your blue influences on it. And so that's also a common criticism that I've encountered when presenting integrated information theory and using it in practice, that people would say, look, you in a neural system, you have that problem that you never really isolate a pure causal interaction. It's always these background interactions. So, and in your framing, it's actually, that's almost like a plus. That's not necessarily a criticism, right? And so I didn't fully catch when you said how to deal with it. So you were saying maybe once the data gets large enough, it's almost like we can average it out, or we can maybe find how the system behaves under different background conditions, because then we have enough observations for different conditions. What would be your answer for that criticism?
Yeah, so I would say that one big assumption sometimes people have who says something like that is that whether the things are totally holistic, so that any parts cannot be understood when it's separated from the whole, right? That's a really extreme view of the holism. And another extreme part is that, oh, no, to understand the whole, you really need to cut into the piece, and then this I can understand, but you can never understand the whole. Both of them are just ridiculous to me. Part of the reason is that, when you think about the neural systems, or how the things works, or how our consciousness works, parts are definitely influenced by the whole to some extent, but it does work independently to some extent as well. Like in the case of the color of the patch, for example, right? Like this part of the patch, as long as we have certain size of the things, and if the uniform, the texture is uniform, you can definitely see things, as they are. But, the ambient light and also, many different things can contextually affect it. Yes, but the quality of this, color patch is definitely more, caused by particular part of the, field. So there is, interaction, yes, but under some condition. But to characterize something, there is, so in a sense, compositionality, right, happening. So some parts of the thing is better described as it is, because things are, manipulated and also, moving or composed in the way that, can make sense in a sense. And so if you take that kind of intermediate view, like, when we are cutting the system, we are cognizant that, under the condition of this kind of, situation, then this part works in this particular way. And then when you combine these parts into the whole, then we have a holistic ideas of how it works. But, many parts are, to some extent, independently moving. Like I can move the left hand independently to the right, but also when I cut my right arm, it will affect on this part. But that's much less, indirect kind of influence. So I don't think many people would go either far, but to some extent, these kind of talks are kind of, marketing kind of talk, right? Like people who can see everything at one time, like an optical imaging, say that, oh, when you are looking at small neuron part, then you never understand the whole. But after looking at everything, what do they do? They just count each of the neurons and then, average out the firing rate or whatever. They don't understand it is. So to understand how the whole works, we need, in a sense, compositional kind of attitude where each of the parts are not treated like this, but more like this.
I find that very convincing. I don't know if we have time, but so my last question, you mentioned relations when you when you talked about these different possible mechanisms that you could find even in the simple two neuron scenario, and so I'd like to maybe see if you can divulge your intuition a little bit there in terms of what do you see. So it's pretty clear what a mechanism is in this very simple example, but what a relation would be and how it might translate to other observables, maybe like correlation or interactions between neurons that we're more familiar with.
Right. Okay. So that's a bit more kind of involved kind of stuff, right? So let me redraw that. Yeah. So one thing that probably so the relation is just to briefly explain what it is. When we are talking about let's say two neuron system like A and B, then according to IIT formulation, this part we need to skip. But if you watch our tutorial or our paper like here, it can be understood that there can be three potential mechanisms, and then each of the mechanism can have a potential so-called purview or sort of spheres of influence. So in the case of mechanism A, usually A affects on B, or A is affected by B from the past, and the B can be also affected by A and can affect on A, and the AB can be affected by primarily A and primarily affect on B or something like that, let's say, right? And then in this case, usual thinking of synchrony or correlation wise, because A is affected primarily by B and B is primarily affected by A, you wouldn't expect this to happen at all, right? In this situation. But it may or may not be the case. That's the important thing to realize. Why this divergence between the standard synchrony or correlation kind of idea versus IIT idea can diverge strongly. The reason is that as we kind of mentioned a little bit, it is IIT sort of the fundamental kind of idea is to consider AB's state as 0, 0 or on off or on off on and on and so on, and then how this affects on the future state of A and B. So this is a kind of so-called TPM, transition probability matrix, and from this they infer this kind of causal diagram. But what these actually do is, rather than if A is like this kind of firing rate and the B's firing rate is like this, they take entire data sequence of A and B together, and then spits out one value of synchrony or correlation. Okay, so here, if it turns out that most of the situation A and B are 0, 0, right here, and it's very likely to be the case for the actual real neuron recording, right? Neurons are not firing any most of the time. Then, if you don't take care of that, then correlation wise, the data is dominated by this 0, 0 situation. And then if 0, 0 leads to the prediction of A equals 0 and B equals 0 in the next step for really high probability, then that leads to some kind of causal relations. But in the case of IIT, the so-called maximum entropy assumption puts all these three situations on the equal foot, because according to their formalism, each moment where it comes from cannot be, inferred from the system's intrinsic view, which is consistent with our kind of conscious experience as well. Our conscious experience is never be sure whether it came from this past or this, future. But that's, sort of assumption. Anyway, so if you take that, point, then these four situations should be equally kind of considered. But the empirical observation is completely, dominated by the actually what observed, right? So it may be the case that, even this is a causal diagram, according to IIT, synchrony could be extremely high and correlation could be extremely high in this system, even though there is nothing common in, A and B is receiving. But empirically demonstrating that has not been done. So, that's something that we should do.
Yeah, very interesting. That's very helpful. Yeah, thank you so much.
Yeah. So this part is probably quite counterintuitive, right? And also this is the assumption that we probably have to make. And, I'm not sure whether other neuroscientists would be also, finding this to be more useful or not. But I think this is actually an important kind of philosophical standpoint, because what actually is only, considered from this kind of thinking, like, whether the vegetative looking like, patients who are not responsive to anything are conscious or potentially conscious. You need to take this type of the view, right? Like if we activate parts of the brain in some way, then they can come out from this, completely like, static kind of situation. But if you just, rely on the observation, this completely flat activation implies that, oh, they are not really, conscious. But what the system actually is only revealed by perturbation of the proper way. And when you get into some kind of attractor state, even us, all of us can fall into sleep or can fall into, anesthetized, situation. So, to understand it, the potential, mechanism of the system is important. And so relying on all these, empirically observed value only kind of thing to potential of the system, that's a sort of that. Yeah, I would say this is a sort of transition from empirical neuroscience into sort of structuralism kind of view of the neuroscience. And that's what I'm trying to also propose, right? Looking beyond what you can see superficially. The structuralism of the Levi-Strauss and so on, Levi-Strauss and so on. I don't know whether that was too much, but
no, I think the part that I'm following, I think this should be interesting to people, even if they're not interested in consciousness per se, because I think that that there's, at least we have an intuition that some of these some of this is relevant for just how brain function in general, right? So
yeah, I think so too. Both compositional kind of thinking and also structuralistic kind of thinking is relevant, right?
Yeah.
And
I have a little bit also the feeling that it's timely. I think because, as you said, neuroscientists are starting to look at the brain differently. You rightfully criticized this approach of just measuring an isolated neuron and treating it as such. And with the advance of new technologies, this has profoundly changed. And so a lot of the old ways that we analyze data and think about data, they still stem from the times where we only had one neuron or one brain area. And so I think we are in need of this new thinking and these new techniques to also deal with the fact that we are now able to measure brain activity much more multidimensional.
Yeah, I actually also encountered a couple of collaborators or potential collaborators who were thinking of, using, neuropixel or optical imaging, but as a neurophysiologist, right? But they said that, all they can do is either PCA or decoding or averaging.
Exactly.
Right? And so, now is the time really to, to collaborate, to promote the collaboration between the theorists and also experimentalists, and both category theory, IIT, or something inspired from some quantum mechanism can be also quite relevant for that kind of collaboration.
That's my intuition, and so yeah, to me this seems to be the future.
Okay.
And yeah, so
great.
exciting.
Yeah, so that's probably good enough for today's conversation, and we'll upload it later. All right. So I'll just finish recording for now.